So here is our very first um, proving trig identities problem. Yes, Annie. So here, like I was saying before, we want to choose the more complex side to work with to eventually equal the less complex side. So right now, this left-hand side is a more complex side. So that's the side that I will be altering or changing. What did I say is a solid first move to make, or a solid move to make in general, whenever you're stuck? Right. Change your functions to be written instead in terms of sine and cosine. Exactly. So right now on the left-hand side, I have a cosecant. I can change that to be 1 over sine of x. And this is literally an identity. If I'm looking at my sheet, it is one of the reciprocal identities. Cosecant of x is equal, or cosecant of tangent. Oh my God. Cosecant of theta is equal to 1 over sine. So I rewrite it. I keep cosine the same. I'm not changing that. How can this be simplified? Ah, yeah, right. 1 over sine of x times cosine of x. The cosine of x goes in the numerator. How can this be simplified? What do you know cosine over sine is equivalent to? Ah, yes, cotangent. And that again is literally an identity. This time it's a quotient identity. Cosine over sine is equal to cotangent, which I should have been looking at this right hand side the entire with. I have now set my left hand side equal to my right hand side, and I have proved this identity. That's it. That is the general process behind proving these equations, proving these identities. So the rest of the class is just going to be me trying to fix as many examples as possible. I don't think that I want to do this next one because it's extremely similar to the one that we just did, right? Or just, I guess I'll do it just really, really quickly. But I want to get to the more complex one. So this, I rewrite secant as 1 over cosine of x. Then this simplifies to sine of x over cosine of x, which simplifies to tangent of x by the quotient identity. And I'm done. Check error. Any questions so far on these either? So right before class, I went through and a lot of the problems on here are, well, I would say 6 of the problems on your math itself are just simple. Um, some of them are harder. Some of them are just a little harder, more like the ones with the don't get when you look at these answers, you're going to have different problems than I did. All right. Number 3, we are going to be working on, again, the left-hand side because it is a more complex side. Now, before you start it, before you start doing anything, you really should look, are either of these two terms, are either of these binomials a trig identity? So is secant x minus 1 or secant x plus 1, are either of those trig identities on our? I know there's a lot here, but I'll actually give you guys a hint. We are not using any of the bottom half identities until next week. So ignore from double angle identities down. Actually, wow. Ignore from sum of angles down. We're only looking at the top three rows. Reciprocal, then Pythagorean, then cofunction. That's what we're looking at. So I'll just tell you, there are no identities that help us with these two binomials. So instead, what I can do to try to simplify things is I can multiply these two binomials together. Now notice, they are the exact same thing, except one has a minus, one has a plus. This is difference of squares. I know that this is going to end up being secant squared of x minus 1. Oh, why am I doing that? You don't have to write it. I mean, it's not wrong if you write it, but it's just writing. You don't have to write it at the end. Now, yes, you can rewrite secant squared of x in terms of sine and cosine. However, becoming familiar with identities, this should trigger something in your brain. Or does this look similar to something we've seen previously on our reference sheet? Let me go to. Yes, it is a Pythagorean identity. Now, it may look exactly like these, but because these Pythagorean identities hold true, they hold true for these exact equations shuffled around a bit as well. Meaning that sine squared of theta is equal to 1 minus cosine squared of theta as well. All, yes, close. Yes, we have to subtract the 1 over. So that's what I was getting. Yes, exactly. Exactly. So I was just showing you that we can shuffle these values around to equal what we want them to equal. So here on the first trig identity, this first Pythagorean identity, if I subtract cosine over, sine squared of theta is equal to 1 minus cosine squared of theta. Also, cosine squared of theta is equal to 1 minus sine squared of theta. The middle identity shuffled around gives us that tangent squared of theta is equal to secant squared of theta minus 1, which, oh my gosh, that's what we did in our class. And also the third one can be shuffled to give us cotangent squared theta is equal to cosecant squared of theta. This one. I would recommend writing these down. I think I told you last class to write them down, but if not, I would recommend writing them down now. Because these will be used just as much as the original Pythagorean identity. These three. Okay. So back over to our problem. We just learned that secant squared of x minus 1 is actually equivalent to what? Thank you. Or tangent squared of x, exactly. Which is exactly what we were trying to end up with. So we're done. Math Excel will also ask you, instead of having you write in this last step, I mean, they'll give you this first equation, right? This whole thing. So it'd be pointless to have you type in this last step because you could get it from the original equation. Instead, what they'll ask is, how does secant squared of x minus 1 simplify to tangent squared of x? And what you'll write is, or what you'll pick, it's multiple choice. You'll pick Pythagorean identity. Whoops. So that's how math Excel works. Any questions on this one? Okay. Number 4. So you're working on the left-hand side. Again, you should like just quickly check to see if any of these are Trig identity, which I'm telling you right now they're not. So it means we need to resort to other things. View. It's not really view. You'll see. It's nice. What I'm going to do, a solid first move to make, is to rewrite everything in terms of sine and cosine. So the things that are not sine and cosine are tangent and cotangent. I am going to tangent to sine squared of x over cosine squared of x. This is a quotient identity times cosine squared of x. Plus, I'm going to change cotangent to cos cosine squared of x over sine squared of x times sine squared of x. Now this is actually, as soon as you change those things, something in your brain should be triggered. You should be like, oh my gosh, look at that. What am I talking about? Ah, we have now created fractions where the denominators will cancel, right? Because if I have sine squared of x over cosine squared of x times cosine squared of x, that cosine squared of x is actually in our numerator. Whenever you have a like term multiplied between the numerator and denominator, it will cancel. Same thing here. The sine squared cancel, leaving me with just sine squared x plus cosine squared x. Now, great. These are in terms of sine and cosine. It's a great thing to now check identity. Ah, where'd you find that, Jack? Yes. Like I was saying, the Pythagorean identities will pop up constant. So that's a great place to be looking. The first Pythagorean identity states that if sine squared of theta plus cosine squared of theta, if those two trig functions are added together squared, they equal 1. So this whole thing actually simplifies down to 1, which is what the right-hand side of our equation wanted. So again, Math Excel won't ask you to type in 1. What they'll ask you to do is type in what identity helped you simplify to 1. And you would say Pythagorean identity. Do you need to, like if you were in class proving these identities, would you need to write that down? I'm just saying that this is what you'll need to input. That's not needed in the. All right. So I want to get at least 340. Wonderful. Because I only have 3 more that I want to do. Do I want to do this one? Really? Yeah. Okay. So on this one, the left-hand side and right-hand side look equally complex. Here, though, I would actually choose, now this is a preference. You can choose whichever side you want, really. Um, I would choose the left, exactly, because I know how to make 2 terms into a single term with multiplication. So I'm going to work on the left. First step, whenever I'm stuck, change everything into terms of sine and cosine. So tangent of theta becomes sine of theta over cosine of theta. Cotangent becomes cosine of theta over sine of theta. Now, like I was saying, the right-hand side is a single multiplied. So how can I make these 2 fractions into a single multiplied term? Or a single term in general? Yes, we can get a common denominator in the upper. So over here, I'm going to multiply this by the other denominator, sine of theta, and I'm going to multiply this by the other denominator, cosine of theta. So what I'm going to do is I'm going to multiply again. My numerator becomes sine squared of theta plus cosine squared of theta over sine of theta times squared. So great. Everything is in terms of sine and cosine. Now is the time to look for an identity. Do I see an identity either in the numerator or the denominator here? What about the left? Have we checked out? Yes. The top, the numerator is 1 because of what identity? What type of identity? It's another Pythagorean identity. The first one, right? We know that sine squared of theta plus cosine of theta is to 1. So that whole numerator is just 1. What is going on? What the heck? So now I know what I'm going to end up with cosecant of theta times secant of theta. Those are the reciprocals of sine and cosine. So all you have to do is split this into two separate fractions. So now it's more obvious. Oh, 1 over, I'm sorry, 1 over sine of theta is equivalent to cosecant. Oh my gosh, saying too many functions today. 1 over sine of theta is equivalent to cosecant of theta. And 1 over cosine of theta is equivalent to secant of theta, which, let's check, is exactly what I was trying to end up. You should be constantly referring to the other side of your equation, so you're working in the right direction. They will. Right now, right now, right now they will. Okay, in this unit they will. We're not going to like curveball at you saying prove this identity, and they won't be equal. All right, that's like mean. That's mean. You'll just be sitting there for hours, like I can't get the left side to equal the right side. What is going on? We won't do that to you. So if you come across one that you're like, oh, the left doesn't equal the right, you did something wrong. You did something wrong. Okay, so over here, I do want to get this one done. I know it looks crazy, um, but it's actually pretty satisfying to solve this one. So what we're doing here is we're trying to take 1 over secant x minus 1 plus 1 over secant x plus 1. And we're trying to figure out, does it equal A or B? So we're unsure what our right-hand side of the equation is equal to. So this does make this a little bit more challenging. But we start out the exact same way. I'm going to rewrite it. I always check, is anything in this a Pythagorean identity? And so that we don't waste time, I'm going to tell you it's not. Because anything with 1 in it, you would be tempted to say the Pythagorean identity, but Pythagorean identities are always your functions squared. So no, none of this is the second identity. So what you're going to do instead is you're going to try to combine them. How can we combine them? We've already done it multiple times. This is like a try to method. How do we combine into one term? Common denominator, yeah. So I'm going to multiply this side by the other's denominator of secant x plus 1 over secant x plus 1. This side by secant x minus 1 over secant x minus 1. Now this is great. This is great. Because what do we recognize our denominator is going to become? Or what should we recognize here? What is the denominator going to multiply to? Yes. So it starts as secant squared of x minus 1. Negative 1 times 1 is 1. This denominator oh, is difference of squares. It's actually, like smooth brain. It's actually just an example of difference of squares. Even though, oh my gosh, we have a Trig, it doesn't change what we know about math. It's just difference of squares. Okay, now what I'm going to do is I'm going to combine like terms in the numerator. 1 minus 1 cancels. And what does secant of x become? Secant x plus secant x. Yeah, it becomes 2 secant x. Now, what do we notice about this number? I have a squared term and I have a 1. What should that immediately make us think about? I have a squared function and a 1. Oh, I should immediately think about the Pythagorean identity. What is secant squared x minus 1 equivalent to? Yes. Okay. So tangent squared of x. So now I'm at a stopping point. None of these are identities, but I know that whenever I'm stuck, I can look and change everything into terms of sine and cosine. That's what I'm going to do. Secant x is, or 2 secant x is equivalent to 1 over 2 cosine x. All over tangent squared of x is equivalent to sine squared of x over tangent squared. Oh my gosh, what am I saying? Cosine squared of x. Now, I should be extremely happy. Why should I be happy? Or at least I'm happy. What is this? What is this thing? It's a thing. Great. Ah, yes. It's a big fraction. We know how to deal with big fractions. How do we deal with big fractions? You multiply by the reciprocal. Love it. So easy. We should love fractions. Uh-oh. What happened? So now I'm actually extremely happy again. Why am I extremely happy again? What do you see? What do you notice? What thing? Ah, I have a cosine in the numerator and a cosine in the denominator, meaning I can cancel a cosine. So this becomes running out of this becomes cosine of x over 2, that 2 still there, 2 times sine squared of x. Now, this part is a little bit tricky. It's just a little bit tricky, and I'm just going to tell you, I'm trying to get to one of these, right? I know that sine squared of x actually 2 sines multiplied together. Understanding this allows me to better see that I can split this into 2 separate fractions multiplied together, right? You can split this into cosine of x over 2 sine of x times, anything can be multiplied by 1, so times 1 over sine of x. The reason I do this is because at this point, when I'm here, I should have at this point realized that A has to be my answer. A has to be my answer. Because I have 2 signs in the denominator, splitting them apart means that I have cosine over sine, 1 over sine. This is equivalent to 2 cotangent x times cosecant x. So my answer is A. This is a hard problem, I understand. And I wanted to show you. Will you have one this hard on your magic? At least I did when I solved mine. What crazy person found this out? I did. No. It's just playing around. It's just like doing a puzzle. I find it fun. You can try a puzzle. You can try to fit a piece and it doesn't quite work, so you have to try another. That's what this is. Who sat down willingly to learn? All right, I do want to do one more. I know I'm holding you after, but I do really, really want to get this last concept, this number 7. Who approved this to be taught to everyone? Um, Trig identities is like a huge, huge part of higher math. So that's why we're learning it. Sudoku to actual puzzle. This is insane. All right. I'm going to work on this one. Last one I'm going to solve for you. We know that solid first move to make is to rewrite everything in terms of sine and cosine. So that's what I'm going to do here. I'm going to change cosecant of x to be, whoops, to be 1 over sine of x minus cosine of x over sine of x. And this is wonderful because look, I already have a common denominator. This simplifies right down to cosine of x, 1 minus cosine of x over sine of x. Math. Okay, so this is exactly why I wanted to go over this. I'm stuck, right? I'm at a stopping point. I changed everything to sine and cosine. None of this is an identity. I need to come up with a different strategy. One thing that you can do is, well, maybe let me ask you. Let me ask you. What could I do here? Just flip it. No, no. Can't just flip something. This is really hard, but maybe I won't wait for you to answer because we do want to finish on time. Whenever you talk like this and you notice you end up equaling a fraction, one of the tricks, it's not really a trick, but one thing that you can do is multiply by what you're trying to get to's denominator. So here, I'm going to multiply this whole thing by 1 plus cosine x over 1 plus cosine of x. Basically, what I'm doing here is I'm trying to force my denominator to be closer to the denominator I'm trying to end up with. That's my thought process behind this. Also, as soon as I lay these out next to each other, I realize that the numerator is actually difference of squares, right? When I multiply the numerators together, I end up with 1 minus cosine squared of x. Oh my gosh. And then as soon as I write that, I have a squared trig function with a 1. What should I think about? Yes, Annie. When I have a 1 and a squared function, you should immediately be thinking about what type of identity. Oh, my goodness. I'm going to keep these separate because remember the denominator separate because remember I'm trying to get to 1 plus cosine of x. I'm not trying to get rid of it. I'm not trying to distribute in. So I'm going to leave them separate for now. Yes, you think about whenever you have a 1 and a squared trig function, you should think of the Pythagorean identities. And when I look at my Pythagorean identities, I see 1 minus cosine squared of x or cosine squared of theta is equal to sine squared of theta or sine squared of x. So that whole numerator is sine squared of theta. Oh, what did I do? What am I doing? It's x, Miss Sunderland. What else do I notice? I have a sign in both numerator and denominator. They so nicely cancel, leaving me with sine of x over 1 plus cosine of x. And oh my goodness, all of that work and guessing paid off. I have sine of x over 1 plus cosine of x. Oh, what the heck was I writing? And I'm done. I'm sure like some of you will hate this, but I'm hoping that a few of you in here are like, this is so fun. This is like a puzzle. This is working with math that one side equals the other. I love it. I love it personally. But you don't have to love it. You just have to do it. All right.